Hi everyone, I'm Tao Zhuang from Tencent. This is a remote, pre-recorded talk, and today I want to walk you through efficient parametric light maps. It's a light map representation that adds a bit of runtime relighting, and for most light maps, it lets us drop the dedicated chroma storage entirely. So let's dive in. So light maps are still the workhorse for global illumination on constrained hardware, and the reason really comes down to runtime cost. Because they're pre-computed, the runtime cost is extremely low and very predictable, and that's exactly what you want on mobile GPUs and standalone VR. But they also come with two stubborn limitations. The first one is that they're completely static. You can't even do something as simple as a time of day sky change. And the second one is storage. If you want to support many lighting scenarios, you have to bake a separate light map set for each one. So your storage just grows with the number of scenarios. So what we're aiming for is a practical middle ground. We want a bit of runtime relighting plus big storage savings, and we want all of that without ever leaving the standard light map baking pipeline. So EPL really comes down to three ideas, and we combine them into a single representation. So the first idea is what we call a parametric decomposition. We bake three separate components: local, sky, and directional indirect. And then at runtime, we just relight them with scalar weights. Now the second idea, and this is really the core novelty here, it's luminance-driven chroma prediction. Instead of storing the color, we predict it from the luminance we already have, and we do that with two predictors, GHG and MHG. And the third idea is an RGBV encoding. That's a perceptual luminance channel, and we calibrate it to each light map's own statistics. So here's the payoff. Around 80% of light maps end up storing no chroma at all. We get about 6 dB higher PSNR than storing chroma explicitly, and the runtime cost is basically free. Okay, let's take those three ideas one at a time. We start from the diffuse reflection integral, and just to be clear, all the light transport recursion is already resolved at bake time. So here's that integral. The outgoing radiance is just the incident lighting times the transport term integrated over the hemisphere. Now the key step is to take the incident lighting and decompose it into a small basis with scalar weights we can set at runtime. And once we do that, the outgoing radiance becomes just a weighted sum of per component light maps. It's the weight LK times the component TK. So relighting is really nothing more than a per component scalar multiply and a sum, which means the shader cost is tiny. In practice, we use three components. There's a local term for indoor lamps and emitters, a sky term that's mostly blue, and a directional indirect term that carries the warm bounce light. And here's the property that really matters. Each component has much simpler color than the sum of all of them. The sky is blue, the indirect is warm. And that's exactly the precondition that lets us predict chroma per component later on. So here's what that reweighting actually buys us on the village production scene, and this is lighting only. On the left, we have the daytime weights with a strong sky and strong directional indirect, and on the right, we have the night weights. Now the sky and directional are turned down, and the warm local term is what stays. And the only thing that changed here is the three scalar weights. There's no relighting, no moving lights, no recomputing chroma. That also sets the boundary of what we do. It's scalar intensity, not arbitrary relighting. Okay, now the core idea. Why is it that we can predict chroma at all? Well, in every light map we measured, the chroma tends to track the luminance. And I want to be upfront here. This is an empirical observation. It's not a strict law. Roughly, why does it happen? Broadband albedos near neutral light sources and bounced light all tend to keep the color weak. So the chroma mostly just follows the local albedo and it varies slowly, and that's exactly the regime where Luma-driven prediction works well. And video codecs already take advantage of this. AV1, for instance, has a chroma from Luma mode. So what we do is bring chroma from Luma over to HDR Lightmaps, but with two twists. First, we fit global plus spatially varying hue gradients at the scene level. And second, we predict from the encoded visual luminance V rather than from frequency residuals. And the result is that around 80% of the Sponza light maps need no chroma storage at all. Okay, so for storage, we encode the luminance into a single visual luminance channel, which we call V. This is the encode, and it's just one analytic expression. And this is its exact inverse, the decode. There's really only one parameter here, and that's S. So that parameter S trades precision between the shadows and the highlights. You can think of it kind of like an exposure knob. And when S is 0, it reduces exactly to RGBM. We pick S so that the decoder's average matches the light map's RMS luminance. And just as important, V is bounded between 0 and 1. So it's a really well behaved perceptual axis, and we feed it straight into the chroma from Luma Predictor. So RGBV isn't just a storage choice, it's actually what makes the prediction well conditioned. And bilinear interpolation in V-space only costs us 0.07 dB, so it stays safe under GPU texture filtering. And over on the right, you can see the encoding curves along with the relative quantization error for a few different values of S. So the first predictor is the global hue gradient, or GHG. The idea is that we interpolate between two endpoint hues, and that interpolation is driven by a polynomial in the encoded luminance. So concretely, we have two endpoint hues plus a degree 3 polynomial in the encoded luminance, and all of that is shared across the whole light map. We fit it with luminance weighted least squares, and we use PCA to find the hue axis. And the storage is just 2 endpoints plus 4 coefficients. That's 20 bytes no matter what the resolution is. Now degree 3 turns out to be the sweet spot. If you go higher than that, you gain less than 0.2 dB. So on a typical local light map, GHG gets over 50 dB with an error map that's almost completely black. And you're seeing reference, approximation, and error from left to right. Now, when the chroma is spatially complex, a single global gradient just isn't enough. And that's where the moving hue gradient, or MHG, comes in. It's the same lerp form as before, but now the endpoints depend on position. So the endpoint hues vary across space, and we get them by bilinearly interpolating from a low resolution map that's 64 times smaller. And all 4 chroma values pack into a single 4-channel texture, so at runtime it's exactly 1 extra sample. We solve it per light map, again with luminance, weighted least squares, plus a scale invariant log gradient regularizer. And compared to a constant chroma map at the same storage, it cuts the RMSE by 26% on Sponza and by 77% on Village. Here you can see reference, approximation, and error for the local, sky, and directional rows. And notice how the residual errors only hug a few thin seams. So these two predictors come together into one simple decision at bake time. At bake time, we fit GHG first, and if it passes the quality gate, we prune the light map, which means no chroma gets stored at all. Otherwise, we fall back to the MHG parameter map. And the gate here is PSNR of at least 40 dB and delta E under 2.0, which is roughly the just noticeable threshold. So in practice, sponsor prunes 82%, village prunes 81%, and color-rich demo prunes only 7%. And the nice thing is that this rate sits on a stable plateau across thresholds, so it's not just an artifact of tuning. The heat map here shows the pruning rate against the two thresholds, and the navy marker is our actual operating point. Okay, now let's look at the numbers. This table compares EPL against the RGBV explicit baseline. So this top row is sponsor with our predicted method at a 4x4 block. And this is the explicit chroma baseline at a matched bitrate. So at matched bitrate, EPL comes out 5.86 dB better, and it's actually using fewer bits. Now here's the cleaner, more controlled comparison. This is our method at the same 6x6 block as the baseline. And this is the same baseline as before. So now it's the same codec, and we still get 3.67 dB at half the bitrate, and that lets us isolate the benefit of the prediction from the codec itself. Then on village, which is the outdoor production scene, we get plus 2.18 dB. And even on the stress demo, we're still at plus 1.67 dB. So the margin really tracks how hard the chroma is, but the key point is that EPL wins at every operating point. It degrades gracefully, and it never regresses. So let's look at this qualitatively on Sponza. Starting from one single shared baked light map set, EPL reproduces day, dawn, and night just by reweighting. And it matches a fully baked GI reference. That's 42.77 dB at 950 BPP, averaged over all 381 light map groups, and the storage is comparable to a conventional static light map. Now to really probe the worst case, we built a deliberately color-rich demo with multi-colored emitters. The top row here is the reference across day, dawn, and night. And the bottom row is EPL. So here only 7% of the light maps prune, but the MHG fallback absorbs all the hard cases, and EPL still beats the baseline by plus 1.67 dB. And the takeaway is that low pruning does not mean low quality. So does the prediction cost us anything at runtime? To find out, we measured on a Xiaomi 15 Pro, that's a Snapdragon 8 Elite with an Adreno 8030, running a full screen shader at 1600 by 720, captured in RenderDoc and averaged over many replays. We compared three shader variants. The GHG pruned path takes 0 WhoMap samples, the forced MHG path takes 3, and the explicit chroma baseline also takes 3. And if we blend the two EPL paths by the actual prune split, we get 2.030 milliseconds. So that's plus 0.05 milliseconds, or about plus 0.3% over the baseline on Sponsor, and plus 0.6% on Village. So basically, we keep the same runtime budget while removing chroma storage from around 80% of the light maps. Now let me be candid about the limitations. So the global gradient can't fit two spatially contrasting hues, and that's why about 18% of spawns off back to the full MHG map. The decomposition only supports scalar sky and directional intensity, so there's no weather and no moving directional lights. And the per light map encoding parameters can under-allocate precision when there's an extreme dynamic range within a single light map. And finally, our scope here is diffuse irradiance light maps validated on UE5 GPU Lightmaps. And here's a concrete failure case. With two contrasting hues, it drops to 27 dB. So it's correctly kept as an MHG map instead of being pruned. Okay, so to wrap up, first, scalar reweighting of the baked components gives us limited runtime relighting. Second, luminance-driven chroma prediction using GHG and NHG removes chroma storage for about 80% of light maps. And third, we get clearly higher quality than explicit chroma at essentially zero runtime cost. That's up to 5.86 dB better with at most one extra texture sample. So thank you, and I'm happy to take your questions in the live.
All right, are there questions for our author?
Hello, thank you for the talk. So you have like the 20 bytes per pixel on your light map, right? So is your light map compatible with the block compressions like ASTC, or is there how much is the quality loss if you use ASTC?
The 20 bytes is for the GHG predictor, and the whole light maps will drop the chroma. So it's not very compatible to the ASTC method because it stores the whole chroma. So it's just a trade-off. So if you want to save the chroma storage, you need to choose the GHG predictor. If you want to get better quality, it's better to choose the MHG predictor. And for the MHG predictor, the quality is better than the ASTC compressor.
Okay, thank you.
Other questions? Well, I'll step in with one. Do you think this approach has any implications beyond light maps? Have you thought about it for other texturing or lighting applications?
I didn't understand your question very well.
So you've applied this to just light maps. Does this approach have applications beyond light maps for other rendering problems or other texture types?
We just apply this method to the light map because the prediction require that the chroma and luma have some connection. And for the light maps, the light is bounced in the scene, so the chroma and the luminance is changed simultaneously. So the light map is better to use the prediction method. And for arbitrary texture, it may be no the connection between the chroma and the luminance.
Thanks. Other questions? Well, if not, let's thank our speaker once again.
Thank you.